Alrighty, hello and welcome back from your guys' weekend. I am still not in school yet, but we are going to continue to move on. We're going to continue to do some um, some conversions, but this time we're going to make it slightly a little bit more difficult by not just talking about one single unit, but by talking about density again. So remember, density is grams per liter or grams per milliliter or grams per centimeter. Either way, we are going to be going to and from density and molar mass. So we're going to have to somehow change liters into moles and vice versa. Specifically in problems 1 through 3 in your notes, we'll be going from we'll be going from density to molar mass. Man, that slide is a little bit of a mess, but that's okay. We will get through it together. Because it's a conversion, I feel like we're good to just jump right on in. So the density of a gaseous compound containing carbon and oxygen is 1.964 grams per liters at STP. Determine the molar mass of the compound. So again, our first step when doing conversions is to write our number as a fraction. So we are going to write 1.96 as a fraction. 0.964 grams over 1 liter. Remember, when we have the grams per liter, that we want grams in the numerator and 1 liter in the denominator. Notice that it is a gas and it is at STP, so we do get to use our liters to mole conversion, which I highly suggest we do. We are going to want to add in our conversion. Again, using our liters to mole conversion, we're going to put liters on the top, 22.4 liters over 1 mole, which is absolutely great because we end up canceling our liters and getting grams over moles, which is what we want to figure out the molar mass, because remember, molar mass is grams per mole. So again, we're just continuing to do our conversions. And we have 1.964 times 22.4. I am working on the math as we speak. 22.4 times 1.964, giving us 43.994 grams per mole, because remember, our liters canceled, but our moles are on the bottom, and our grams are still on the top. Although we do need to double check our significant figures, specifically my significant figures. This guy's, the amount of significant figures he has is an infinite amount because, yes, it is a conversion factor. And this guy has how many significant figures? 4. Yes, it has 4 significant figures. So our answer should have 4 significant figures as well. It currently has, yes, 5. So in order to drop it down to 4 sig figs, we're just going to drop that 4 off the end, and we get 43.99 grams per mole. Now, we can work backwards, and we can ask, what is the density of a gas? Remember, we can go from moles to liters. Liters is an acceptable unit. Grams per liters is an acceptable unit for density. We don't have to go any further than that unless specified, but it's not. So we are going to start and just go to, we're going to start with molar mass and go to density with just liters. Now you're like, Mr. Cotton, there are no numbers, so I'm not sure what to use first. But again, if we're starting with our molar mass, because we're going from molar mass to density, all you have to do to find the molar mass is look at the periodic table and round to the first decimal point. So we are looking for krypton on the periodic table. Out of curiosity, somebody remind me hopefully you guys are reminding yourselves of maybe what family krypton is in. That's right, it is in the noble gas family. Normally they don't play well with anybody. They don't bond or do any sort of fun things, but we can still talk about their density and their molar mass. Krypton's molar mass is 83.0 83.8. Remember, our molar mass is grams per mole, so 83.8 grams over 1 mole for krypton, or Kr. Okay. We are going to then do what? What unit should we focus on? Right, we should focus on changing the mole to a liter. We want to focus on changing a mole to a liter, because if we can get grams per liters, that will give us a version of density, and then we can be done. Again, we do have a conversion to go from moles to liters, thank goodness. So we're going to use that conversion from our little sheet that I gave you guys way back when I hadn't left yet. And what was that, Wednesday? And yeah, so we're going to use that conversion. So 22.4 liters, this time the 22.4 liters is going to go on the bottom. Why would we want to put 22.4 liters on the bottom? The liters don't cancel with anything. Right, it's because we want the moles to go on the top, because we do want our moles to cancel. And they do, because we have one on the top and one on the bottom, leaving us unit-wise with grams over liters, which is a version of density, and I do like that. So let's go ahead and do our math, which is 83.8 divided by 22.4, giving us 3.74. You might say, Mr. Cotton, how do you know for sure how many sig figs we need? Well, we're looking at our molar mass because that's the number that we were technically given. Now, I know you're like, we weren't given that, but we do know that molar mass is whatever we're given from the periodic table rounded to the first decimal place. So we do know for sure that we were supposed to have 3 sig figs for this specific this specific problem for our krypton's molar mass. So then we are also going to have 3 sig figs in our answer for the density of krypton. So yes, we are just flipping back and forth from density to molar mass, and then not comparing the two, but using our 22.4 liters conversion. All right, moving on. I do have a little bit of a fun problem, because not only are we going to work our densities into molar masses, but then we get to look at the periodic table and try and figure out what molar masses fit sulfur dioxide, ammonia, chlorine, nitrogen, or methane. Notice that there are 1, 2, 3, 4, 5 compounds, but there are only 3 densities, meaning there are extra options in terms of extra compounds that don't have densities. So we're really going to have to make sure that we are getting the molar mass correct, because we could be getting the complete wrong one and leaving something out that we could have picked for the correct answer. But before we get too crazy, let's first take our densities and turn them into molar masses, because that's what the problem is asking us to do first. Calculate the molar mass for each substance. So let's say that this is A, this is B, and this one's C. Then after we've calculated the molar masses, then we can start identifying them based on their periodic table molar masses. So let's start with A. We're going to have 1.25 grams per liter over 1? No, we want to do over 1 liter. Again, that gives us grams on the top, liters on the bottom. We want to go from density to molar mass. Molar mass is grams per mole, so we want to get rid of our liters and substitute in a mole. So we're going to put 22.4 liters on top, because we want our liters to cancel, and we know that 22 liters is also equal to 1 mole. This is another example of a great opportunity, because we have grams over moles, which is exactly what we want for molar mass. We end up getting 1.25 times 22.4, a perfect even 28. But we are going to give it a 0.0, because we do need 3 significant figures. Please don't forget, 3 significant figures in the beginning, 3 significant figures in the end. Even if it comes out to be perfectly even, we do need that 0.8 decimal. And our units are grams per mole. All right, so let's label this one A, and then we will do B. B's is a little larger, a little heavier density, so 2.86 grams, again over 1 liter. We're going to do the same exact process because, again, we want our liters to cancel, and we want moles on the bottom. And that, again, happens nicely for us here. We're going to take 22.4 times 2.86, this time getting 64, which is a larger molar mass, and that's kind of cool. We need 3 sig figs, so 64.1 because it's 0.6, and so that 6 rounds a 0 up to a 1. Again, our units are grams per mole since that was left for us, grams over moles. Okay, last but not least, in terms of changing our densities to molar masses, we have C, a little bit of a small density here, 0.714 grams over liters, times, again, our same exact conversion. I know it feels redundant, but it's a nice good practice for you guys to get used to going from density to molar mass. Just a slight conversion. Okay, again, we want to make sure that our liters cancel and we are left with grams per mole, and we are, so that's super nice. This time we're taking 22.4 times 0.714, giving us almost exactly 16.0, I'm sorry, because it was 15.99, but with that 9 we'll round the second 9 up to a 0, which will give us the 16 instead of a 15. And again, our units are grams per mole. Now, what we're going to do to figure out the rest of this question is look at ammonia, sulfur dioxide, chlorine, nitrogen, methane, and C, what their molar masses are. Remember that some of these are going to be diatomics. Also, if you're not sure what ammonia is, you can always Google it if you'd like. It is NH3. Okay, so NH3 or ammonia, and I'm going to write that off to the side and draw an arrow to it. Yay, NH3 or ammonia, if we're finding the molar mass of ammonia, is 14.0 plus 1.0 plus 1.0 plus 1.0, because there are 3 hydrogen, and hydrogen's molar mass is 1.0. This ends up giving us 17.0, and 16 is kind of close, but I would like to wait a minute and see if we can get something even closer to 16 before assigning ammonia to C. So 17.0 grams per mole. And I'm gonna go ahead and erase this work. I know it's quick, but because it's a video, you can pause it if you need to and rewind. And I'm gonna get rid of that arrow. Bye, arrow. Okay. Sulfur dioxide. Hopefully we know sulfur dioxide is SO2, sulfur dioxide, di meaning 2, oxide meaning oxygens. Sulfur dioxide would have 32.1 grams per mole for sulfur, plus 16.0 plus 16.0, since oxygen's molar mass is 16.0 and there are 2 of them. We end up getting, oh Lord, I'm going to have to use the calculator for this one. I'm not as quick as I used to be. 64.1, which, ding, 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 we do have a winner. We have something that exactly matches our number or letter B. So I would argue that sulfur dioxide, not argue, we are coming to the full conclusion that B is sulfur dioxide for sure. All right, I'm going to erase this again. You can pause if you need to and go backwards because I am maybe going a little quick, but we'd love a good pause session to allow you to work as much as you need. Again, if you're just now hearing this, feel free to pause or rewind or do anything at any point because this is a video and I'm hoping you guys get as much out of this because I am not going to be here at all today, but I should be back tomorrow to answer all your burning questions. Okay, chlorine. Chlorine has a, I believe, if I'm not mistaken, I got to look at my periodic table real quick. Yes, has a molar mass of 35.5 But if we hopefully remember, chlorine is a diatomic. So we get 35.5 plus 35.5 because there are 2 chlorines. This will end up giving us 71.0, which is not really close to any of ours. So wah wah, sad day, probably not an answer. That does mean, hopefully, that the last 2 match with the things that we have left. Nitrogen is another diatomic, tricky. This time we have nitrogen's molar mass, which is 14. Since it's a diatomic, we get another 14. And we end up getting 28.0, which ding, 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 we found another match in gas number A, or letter A. So we can say that gas A is absolutely, based off its density and conversions to molar mass, nitrogen gas. Which, if we are, if Mr. Cotton set this all up right, then we should have the final gas being C. Let's go ahead and double check ourselves. I am going to mark it there because I don't make mistakes. But I am going to go ahead and mark it there, and let's do it together. So carbon has a molar mass of 12.0. Hydrogen has a molar mass of 1.0, but it is there 4 times. So we are going to put it there 4 times. 12 plus 1 plus 1 plus 1 plus 1 is going to equal 16.0 grams per mole. And ding, 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 we do have a winner for our substance C in methane, since it is the lightest molar mass and the lightest density of the group. So A is nitrogen, B is sulfur dioxide, and C is methane. And we have solved this problem when we were only given densities because we can turn density into molar mass and then check the periodic table and see what the periodic table tells us about each of the compounds' molar mass. Now, this is only going to be video 1. I will upload a second video over percent composition. That'll be problems 4 through 7. I am missing a little bit of instruction in your notes, so please make sure to watch the next video because I will talk about how to find percent composition. It's fairly straightforward, but I didn't even give myself an opportunity to talk about it. We just dove straight into practice problems. So if you want to scribble in the note, the margins of your notes, or if you'd just like to make notes on a whole nother sheet of paper for how to do percent error, I think that would be a great idea. If you are feeling like you're just ready to rock the world because this stuff actually seems like it's probably easy, then I would say by all means, you should still probably take notes, honestly, is where I'm at. But up to you guys. I will say I do think you should do the problems after I've gone over what percent comp is and how to find it. So I will see you in the next video where we talk about percent comp and go over problems 4 through 9. They're a little bit more fun, and they can be some super helpful in real world applications. So see you in the next video. Bye.